In this series of discussions on chemical thermodynamics, today in lecture 3, I shall try to explain different aspects of this first law of thermodynamics. This first, I give the statement of this first law of thermodynamics. It is very simple and it is the law of conservation of energy. It means that heat energy can neither be created nor be destroyed. One form of energy can be transformed into equivalent amount of another form of energy. It means that the energy of the universe is fixed or conserved. However, and this is the statement in classical thermodynamics. However, Einstein formulated, and it has been realized also, that the mass could be converted into energy. According to all-time great scientist Einstein's very famous formula, E equal to mc square. But in this classical thermodynamics, this sort of mass energy conversion generally not considered. So we shall discuss the first law of thermodynamics, only considering this conservation of energy of this universe. However, if this conversion has been taken or considered, then total mass and energy both together of this universe will remain conserved. You know, it means that one form of energy could be obtained. If one form of energy disappears, then equivalent amount of another form of energy must reappear. The immediate consequence of this first law of thermodynamics is the rejection of perpetual motion machine of the first kind. We all know the scientists are very imaginative, and the scientist Einstein told in his book, My Views, the imagination is greater than intelligence. So before coming this first law of thermodynamics, scientists imagined that they will construct one engine or machine which will produce the mechanical work for indefinite period of time without supplying any form of energy to this engine. But this is called the perpetual motion machine of this first kind. But this first law statement of this first law of thermodynamics rejects the idea or possibility of construction of such type of machine, as some form of energy must be applied to the engine to get the mechanical work or mechanical energy from this engine. So, if it would be the case, then we do not need petrol, we do not need diesel, we do not need any sort of fuel, and we get this mechanical energy for an indefinite period of time. But this is not possible. Now I like to give the different mathematical forms of this first law of thermodynamics. This mathematical form, unless we shall discuss the mathematical forms, we cannot quantify the statement or the consequences of this first law of thermodynamics. And the mathematical form of the first law of thermodynamics involves the work done, heat transfer, and the internal energy. These three energy terms are connected in the mathematical form of the first law of thermodynamics. Let us consider the system so mathematical formulation of first law of thermodynamics. In brief, I can write a TD. Suppose this is a system of our interest, and this and the rest of this universe is the surrounding. Now let us take this Q amount of heat is supplied to the system, and at the same time W amount of work is done on the system by the surroundings. So the system now the system acquires this heat energy and the mechanical energy in the form of work, and from the surroundings. Naturally, the internal energy of the system must increase, and the sum of the two energy are being absorbed by the system from the surroundings. So the first mathematical statement, I can write this Q equal to Q plus W equal to du. This is the general formulation of the first law of thermodynamics. This Q, very interesting to note, the Q, the heat supplied to the system, this is not an exact quantity. W, work supplied from the surrounding to the system, this is also not exact, but this du, the value of internal energy change for the system, is certainly definite. And this amount of work, this work may be of different types. It may be mechanical, It may be electrical, it may be gravitational, it may be magnetic, or the work coming from this surface tension. But we are in thermodynamics much more interested with this mechanical work, and mechanical work done by the system, as this amount of work we can receive for our own benefit. So let us and not only that, the mechanical work is a very common type of work. And now let us discuss when W is only mechanical work. Mechanical work. Let us consider a cylindrical container, and this is the V1 volume. Here 1 mole of gas is taken as the material, and this is the piston. And we all know this thermodynamic piston is weightless, frictionless, movable. So this suppose Q amount of heat is given to the system. And whenever the heat is applied to the system, here P is kept constant. P is kept constant. So whenever heat is supplied to 1 mole of a gas, the temperature will change from T1 to T2. And according to the Charles law, as the temperature is increased for the fixed amount of this gas, so P remains constant, the volume will also increase from V1 to V2. V1 is the initial volume, V2 is the final volume, T1 is the initial temperature, T2 is the final temperature. One subscript is given to this initial state and 2 subscript is given to this final state. So in this case, this work equal to only mechanical, and this work is minus PdV. Minus PdV, pressure into volume change. And so replacing W, whenever this work is only mechanical, we can write Q minus PdV equal to dE, or second form, mathematical form is Q equal to du plus PdV, and this is the 2. This is a very simple to explain. Q is the amount of heat given to the 1 mole of this gas. Due the it does some mechanical work. The system does some mechanical work which is equal to PdV, and rest amount of this heat is used to increase the internal energy of this system. So this is the second form. Now, whenever we like to calculate this du, change in internal energy, already it is discussed that U is the internal energy of the system internal energy is coming from, this is the internal energy and it originates from the motions of this constituent particles of this system and also interparticle potential energy, interparticle mutual interactions. So this U, say either it is the internal kinetic energy coming from these motions of these constituent particles, and other is internal potential energy. This is coming from this interparticle interactions. This one, so this molecular or particle thermodynamics does not consider the constituent, consider what type of the system is made of, what are the type of constituents, what are their motions or other types. Thermodynamics is a macroscopic science. So this internal energy of this system, it is not possible for this thermodynamics to calculate. Naturally, what we can do whenever the system moves from initial state to final state, there will be change in internal energy, and this change of internal energy we can express in terms of the measurable parameters like heat capacity, like temperature, pressure, volume, mole number, etc., which are measurable. So this, to calculate this du, we may consider U is a function of a temperature and volume. Here, internal energy change occurs due to the change in temperature and due to the change of the volume. Pressure is constant. So according to the partial differentiation, this du equal to del U by del T at a constant volume into dt plus del U divided by del T del V at constant temperature into dV. It means that this is the increase of internal energy for the change of temperature, for this increase of temperature while volume remains constant. This is the internal energy change for the change of volume V2 minus V1 when temperature is constant, and sum of the changes is equal to the total change of this internal energy for the system for the increase of temperature and volume. So we can insert this du in this second mathematical form. So Q equal to del U divided by del T at constant volume into dt plus, whenever this one and this one we shall write, this dv gets common, so it will be the P plus del U by del V at constant temperature into dV, and this is the equation number 3. Now we shall have to give some magnitude of this term and this term in order to quantify the first law of thermodynamics in terms of these measurable properties. And so from this equation number 3, if V equal to V kept constant, means volume have been kept constant, only the temperature is increased, means the system does not do any sort of mechanical work. So in this case, this equation 3, say this QV, heat supplied at constant volume, is equal to del U by del T at constant volume into dt, and this part becomes 0. Dividing by dt, we can write del by del T at constant volume equal to del U by del T at a constant volume. It is to be noted that Q is not a perfectly differential quantity, so we shall not write dq. So this term I can explain. This term is the amount of heat given to the system containing 1 mole of gas for the rise of 1 degree temperature at a constant volume. So according to this one is the CV. CV means constant volume molar heat capacity. Constant volume molar heat capacity. It is the capacity, heat capacity of this gas. And you know, heat capacity, significance of this heat capacity means that how much the heat the system can store up. So it is a measure of this amount of heat it can store up. So if this one is the CV, then this one is also equal to CV, and we can write this Q equal to CV dt plus P plus del U divided by del V at constant temperature into dV, and this is equation number 4. Now we shall see the value of del U by del V. This term yet to be converted into measurable quantities, and this del U del U by del V at constant temperature equal to 0 for ideal gas. I can show in some next lectures. For ideal gas, this term del U by del V at constant temperature equal to 0 means isothermal expansion or compression of this ideal gas. There will be no change of internal energy. So why it is coming so? You know, this internal energy coming from this kinetic motion of these particles, and also the potential energy, internal potential energy. This one totally depends on T, depends on the temperature. So whenever the temperature is fixed, this internal kinetic energy is also fixed. And in case of ideal gas, there is no intermolecular attractions or interparticle attractions, and so for this ideal gas, this term is also equal to 0. So this one I can put here, and then Q equal to CV dt plus P plus for 1 mole ideal gas. This can be taken as a 5A. For n moles of this gas, this Q equal to NCV dt, plus PdV. And in this case, NCV dt plus PdV for n moles gas, n moles ideal gas, and this is taken as 5B. This dV is not changed. This dV is the volume change for 1 mole of this gas, and this dV is the volume change for n moles of this gas. And for van der Waals and for this van der Waals gas, this term is equal to A by V square. In van der Waals gas also, the internal kinetic energy equal to 0 since the temperature is fixed. But in van der Waals gas, there is a interparticle attractions, intermolecular attractions. So with the change of volume, this potential energy due to intermolecular attractions will change. So this one equal to A by V square, where A equal to van der Waals constant, and this constant is originating from the intermolecular attractions. This A of van der Waals equation could be determined experimentally by using the critical constants value of that gas. So thus writing this one, we can have this Q equal to CV dt plus P plus A by V square into dV, and this one for 1 mole van der Waals gas, and this can be taken as a 6A. And for the n moles, this Q equal to NCV dt plus here P plus AN square by V square into dV for n moles van der Waals gas. So these are the forms, different forms of this first law of mathematical forms of this first law of thermodynamics. And one after another we can use in some times of this calculations. Now I can here give also the expressions of this internal energy, expressions of this change in internal energy of this system containing this either ideal gas or the van der Waals gas. And for ideal gas, change in internal energy du equal to this term equal to CV dt or for n modes, n CVDT. This is the first term, and the second term is A by V square, A n square by V square into dV. For ideal gas, this term is n CVDT and this term is equal to 0. So this Q du, change in internal energy, simply could be determined by determining change in temperature, and the CV value could also be determined by means of calorimetry, and n the number of moles of this gas are present in this system. For van der Waals gas, this du equal to n CVDT for this term, and for this term A n square by V square into dV. And these two equations are used to determine the change in internal energy for this ideal gas and the van der Waals gas. These, of course, from this also I am certain, or I can show, this U is a function of temperature only. That means U is a function of temperature only for this ideal gas. But in case of van der Waals gas, this is for van der Waals gas. And for this van der Waals gas, naturally U depends on temperature, U depends on volume. So U is a function of temperature and volume. However, these two equations are very useful, but could not be applied to this reversible phase change, where one state of the substance, one state of aggregation of the substance is converted into another state of aggregations at constant temperature pressure, such that ice melts down into water at 0 degrees centigrade and 1 atmosphere pressure. So for that case, the reversible phase change, reversible phase transitions, this type of equation is not applicable. Further, for chemical transformations, whenever the reaction occurs, in this case also, these two equations are not used for the calculations of a du. Let us now consider some critical cases of this first law of thermodynamics. And the first one, some special cases of the first law. First law of thermodynamics. The first one, let us consider the cyclic process. Cyclic process. Let us first consider the cyclic process. In the case of cyclic process, the system comes up to its original state after passing through the different states. And so, for the cyclic process, cyclic integral of du equal to 0, as u is a state function. This one may not be 0. This cyclic process for this Q and W only will be equal to 0 if the process is reversible, otherwise they may not be 0. But a dQ, whether the process is reversible, irreversible, or whatever may be the path of the system in coming for this cyclic process, this du always will be equal to 0. So in this case, du equal to 0. So q plus w equal to 0 in general. Or q equal to minus w, and this minus w is the work done by the system. On the surroundings. So it implies that whatever the heat energy we supply to this system for the cyclic process, the whole of this heat energy is being converted into what? And this system totally converts this heat into mechanical work. So it is very fruitful, as whenever we try to use this heat energy for getting this mechanical work, we always prefer this cyclic process. Later I will show a case which is very popular, Carnot cycle, Carnot engine, and this this isothermal process. Isothermal process, and this isothermal process T is constant, and so dt equal to 0. Say for ideal gas involving mechanical work, equation number this is 5a. This q equal to dt equal to 0, this term will vanish, so this is equal to pdv. Means work done, in this case also work done by the system, pdv. It means that the heat is being converted and the system will do this mechanical work totally. No heat is hidden up in the form of internal energy of this gas. So whenever we desire for the conversions of heat into mechanical work, we always use the isothermal process, and I can show also in next lectures. Only in isothermal process the maximum amount of work could be done by the system in a reversible process. Means the reversible isothermal process will yield the maximum amount of work. Then third, isoporic process. Isoporic process means V equal to constant, so dV equal to 0. So in this case, whatever may be the ideal gas or real gas, Q equal to, of course, if we consider this ideal gas, that will be better. Ideal gas, V, this one, V is constant and this term equal to 0. So Q equal to CVDT. Or in this case also, I can show in general this Q equal to minus du, means the increase. So whatever the heat energy is given to the system, it will do the internal energy only, and no mechanical work is done. Now next one, this fourth, whatever the heat energy is given to the system, it will increase this internal energy of the system or increase this temperature of the system, but no mechanical work is done. Now this fourth, process occurring in isolated system. Isolated system means in this case there is no interactions between this system and surrounding, or I can say there is no surrounding. There is no surrounding. This is surrounding. This is no surrounding or the environment surrounding these isolated systems. So for this isolated system has no surroundings, so Q equal to 0 and W also equal to 0, and so du equal to 0 or U is constant. U is constant. Means internal energy of this isolated system always remain fixed or conserved, as there is no interactions with the surroundings. And this is the difference between this isolated system and adiabatic system. In case of adiabatic system, the internal energy can be changed, but in case of isolated system, internal energy cannot be changed. Here lies the difference between the adiabatic system and the isolated system. And this fifth, adiabatic process. In case of adiabatic process, the walls of the systems are wrapped by good insulator, so that the heat energy cannot pass or cannot be exchanged between system and surrounding. So this is Q equal to 0. If we consider this equation number 1, then Q equal to 0 means du or minus du equal to, or du equal to minus PdV, or better minus du equal to PdV. PdV again is work done by the system. So whenever any system in adiabatic process does some work, does some pressure volume work or the mechanical work, its internal energy will decrease. Means du equal to severity, its temperature will decrease. And this can be illustrated in better way. Say instead of writing this du, we can write for ideal gas, one more ideal gas, this one equal to severity and this equal to PdV. For one more. So minus Cv and here T2 minus T1 equal to P into V2 minus V1 as given here. So or I can write this Cv T1 minus T2 equal to P into V2 minus V1. Let us discuss or put some comments on the basis of this equation. For adiabatic expansion, this V2 is greater than V1. Means this term becomes positive. P is always positive. So right hand side is positive, means left hand side must also be positive. So T1 must also be greater than T2. What does it mean? For this adiabatic expansion of an ideal gas, there is a fall in temperature. Adiabatic expansion for this ideal gas, there is a fall in temperature. It is very important conclusion. For cooling a gas to come down to its critical state, in order to liquefy this gas, it is usual practice. The gas is processed in adiabatic expansion. As for this adiabatic expansion, there is a fall in temperature. And you can know whenever some gas is escaping from this nozzle will be cooled down. And this conversely, for adiabatic compression of ideal gas, we shall always use this ideal gas for its simplicity. For adiabatic compression, V2 is less than V1, so T2 must be greater than T1 according to this relation. What does it mean? For this, there will be a rise in temperature for this adiabatic compression of this ideal gas. So the temperature will be warmed up, temperature will be increased, the gas will be warmed up by this adiabatic compressions of this gas. I have told earlier that the laws of thermodynamics are coming from this direct human experience, and every conclusions is fully realized in our daily life. For this one, I can cite one example. Suppose we are putting the pressure in a cycle tube by means of a hand syringe. By means of a hand syringe. This here is one bright example in our daily life is that if we put this air pressure in a cycle tube by means of a hand syringe, whenever the hand syringe is operated, the air is compressed and goes to this tube through this valve pin and valve tube. Repeated compression of this air by this syringe will be heated up. This syringe will be heated up so much that it will be very difficult to hold this syringe by this simple hand alone. We require the handkerchief or this cloth to hold this syringe. I have told that Q and W, they are not exact differential or not perfectly differential quantity. though du is a perfectly differential quantity. By several examples, I can show this q and w, they depends on this path. These two are the path functions, but u is a state function. One example I can cite. Suppose one chemical reaction, zinc plus copper sulfate, giving you this zinc sulfate plus copper. This is the initial state and this is the final state. If we run this reaction in a beaker, open beaker, then the amount of heat, whole amount of heat will be liberated, and this reaction will not do any sort of mechanical work. But if we, that means work equal to 0, and totally this q equal to positive, q is liberated. But whenever this same reaction, same coming from this initial state to same final state in a Daniell cell, the amount of electrical energy we can obtain, some amount of heat and some amount of mechanical energy we can obtain. But I like to show, this shows that q and w, they are not perfectly differential quantity. I can show mathematically by using this Euler's reciprocal relations that suppose for this case of q, I can write dq equal to, here dq equal to del u divided by del t at a constant volume into dt plus p plus del u by del v at constant temperature into dv. Let me see, d now I have applied to indicate that q is supposed to be perfectly differential quantity. Now let us consider the Euler's reciprocal relations, whether it is valid for this q or not. So this del q, by keeping this volume fixed, del q by del t at constant volume equal to, here this one is 0, so del u by del t at a constant volume. Now again differentiating this one with respect to volume, keeping temperature fixed, dV, and here a del q by del t at constant volume, and temperature we are fixed, temperature differentiating this one, double differentiation with respect to volume at constant temperature is fixed. This will be equal to del 2u divided by del v and del t, and this is suppose equation number A. And again this one, del q by del v at constant temperature dt equal to 0, this term will vanish, so this will be p plus del u by del v at constant temperature dividing by dv. And now differentiating this one with respect to temperature, del q by del v at constant volume, this v remains constant, this one equal to del p by del t at constant volume plus del 2u divided by del t and del v, and it is the equation number B. If q is to be perfectly differential quantity, then this one and this one must be equal. This one and this one must be equal. U is a perfectly differential quantity, so this term and this term must be same and cancels. So in order to be these two terms equal, this del P divided by del T at constant volume must be equal to 0. But actually, whenever the volume V is kept constant for this gas with increasing temperature, pressure must also be increased. There will be change of pressure. So this cannot be equal to 0. So these two terms are not equal. So Euler's theorem, Euler's reciprocal, relation shows that del by del V, del Q by del T at constant volume and T not equal to del T by del T into del Q by del P at constant temperature into V. So Q is not a perfectly differential quantity. In a similar fashion, I can show this W work done is not a perfectly differential quantity. W equal to defined by PdV, and V is a function of temperature and pressure. So dV equal to del V by del T at constant pressure into dt plus del V by del P at constant temperature into dV. So if we put this term here and do this double differentiations of this W, here I shall write dW, and it could be shown that del 2W divided by del T del P is not equal to del 2W divided by del P del T. Means W does not obey the Euler's reciprocal relation. So this W is not a perfectly differential quantity. These are the two path functions in exact quantity. So this is all about this first law of thermodynamics in good details. Every corner is taken into account. And I thank to you all who are watching this video. Next lecture will be the relations between pressure, volume, temperature in case of adiabatic process for ideal gas. Thank you all.